Hey, Charles.
Hey, Michael, how's it going?
It's not going too badly. I'm kind of excited because what we're going to do in this section is take the previous two sections and kind of mash them up.
Oh, I like that. I always like mashed sections.
So, in particular, we're going to use some of the ideas from convergence to better understand value iteration, linear programming, and policy iteration, three algorithms for solving MDPs. So, I decided we could call it Advanced Algorithmic Analysis, or AAA.
Oh, I like that. And I like that you have a Scarlet A.
Ah, yes.
That's a nice illusion.
That's another A.
Yes.
So last time we were talking about how contraction mappings make it so that value iteration converges, in the limit that we end up solving the Bellman equations. I'm not going to want to say too much more about value iteration, but on one slide, I want to at least summarize a couple interesting things that are worth knowing. All right, so here's the first one. If you think about qt star, so that's the q function that we get if we run value iteration for t star iterations,
Okay.
we know that it converges in the limit. We know that qt eventually goes to q star. But here's kind of an interesting thing that we know about the finite horizon. So there is some t star, less than infinity, that's polynomial in the number of states, the number of actions, the magnitude of the rewards in the reward function, the number of bits of precision that are used to specify the transition probabilities, and 1 over 1 minus gamma. So that if we run value iteration for that many steps, the q function that we get out is q sub t star of SA. If we define a policy, pi SA, which is just the greedy policy with respect to that q function, that policy is optimal. Okay, so what we're saying here is that we know that in the limit, if we run value iteration for an infinite number of steps, then the q function that we get out at that point, the greedy policy with respect to that q function, is optimal. But what this is saying is that there is some time before infinity where we get a q function that's close enough so that if you do the greedy policy with respect to it, it really is optimal, like all the way 100% optimal.
So what that really means is it's polynomial in the things you would expect to matter. And so that's saying that you can actually solve this in a reasonable amount of time.
Yeah.
I mean, anytime I see the word polynomial, I'm like, okay, what you're saying is this is reasonable.
Yeah, now the trick in this particular thing, the reason it's not just polynomial, is this 1 over 1 minus gamma. So as gamma gets close to 1, this blows up, and that's not polynomially bounded in, say, the number of bits that it takes to write down gamma. So it really is exponential in terms of the number of bits it takes to write down the whole problem.
Mm.
But even so, if you take gamma to be some fixed constant, then 1 over 1 minus gamma might be really big, but it's some fixed constant, and we're polynomial in all the rest of this stuff. So what this really all boils down to is the idea that once you fix an MDP and the number of bits of precision that you're using to write it down, then there's going to be some optimal action, and there might be other actions that are tied for optimal in any given state. But the second best action is going to be some actual bounded amount away from optimal. So it can't get arbitrarily close to optimal. It's going to be some distance away. And what that gives us is that when we run value iteration enough, eventually the distance between the best action and the second best action gets bigger than that gap. And once it's bigger than that gap, then the greedy policy is going to be optimal. It's going to choose the actual optimal action in all states.
So VI converges, and it converges in a reasonable amount of time.
Well, it's not that it converges in a reasonable amount of time. The greedy policy with respect to value iteration converges in kind of a reasonable amount of time.
Okay, that's a much better way of saying it. Okay, I buy that.
This turns out to be a consequence of Cramer's rule, which we're not going to talk about, but this is why once we write down everything with polynomial precision, that we are guaranteed to get some fixed size gap between the best and the second best.
It's always amazed me how you manage to get Seinfeld into our conversations.
Kramer rules. So here's another thing that we know. That is, if we run value iteration, we get a series of value functions, say, vt. If we compare the value function we have at some time step t to the same value function that we have one time step later, vt plus 1, that if it basically has stopped changing, if the amount of change from t to t plus 1 is less than epsilon for all states in the MDP, then the largest difference between the optimal value function and the value function that we get, sorry for this, but by taking that value function, taking the greedy policy with respect to that value function, and taking the value function of that greedy policy, is small, right? So we're going to be doing almost optimal from all states. And the smallness here ends up being 2 times that epsilon times gamma divided by 1 minus gamma.
Oh, yeah, sure. That's intuitively obvious.
Well, maybe not intuitively obvious, but the Sing and Yi proof of this is not so complicated, not so different from the stuff that we've been doing. And you get the 1 over 1 minus gamma because this little bit of epsilon that we could be off could get magnified over every single step as we think about this into the future. That's why we get a 1 minus gamma in the denominator.
Mm-hmm.
And then, 2 epsilon, because I don't know which side of the epsilon we're on, times gamma, because it doesn't take place right away. It's one step from now. So it does kind of make sense. But the real important upshot of this is the notion that if you can get a good enough approximation of the value function, then you're going to have a good enough, well, then you can at least put a bound on how far off you are in terms of following the resulting policy from how far that's going to be from optimal. And furthermore, we don't even need to know how close we are to V star. All we need for this result to hold is we look at 2 consecutive iterations of value iteration, right? Which that we have. We're running value iteration. We know what it was a step ago. We know what it is now. And so we can compute this epsilon, and that gives us a bound on what if we just stop now and follow that policy. So that's a really useful thing. Otherwise, knowing that value iteration converges in the limit is not super duper helpful because you're never going to get to the limit. And knowing that value iteration eventually is optimal, even if finite, is still not that helpful because you don't know when that takes place. So what this is telling us is we can actually test on our own when is a decent time to stop.
So that's cool. So here's something I just noticed. If I look at both your 1 and 2, I noticed that they both would encourage you to pick small gammas. Right?
Yes, it is certainly the case that if gamma is really tiny, like gamma is 0, then this bound stays small, this bound stays small. It's all good. The closer gamma gets to 1, the more things are problematic. But what do you infer from that?
Well, mainly, why is that? Well, that's because gamma really tells you what your horizon is. And so the smaller gamma is, the sort of further into the future you don't look. If that makes sense. And so that makes sense then, right? That if I'm not really worried about the future, then it doesn't take much for me to be doing what appears to be optimal.
Yes, that's right. Right. It's easy to optimize over a very short horizon. And the horizon, the effective horizon is always something like 1 over 1 minus gamma. That's kind of how far into the future do rewards actually matter.
Right.
And so, right. So gamma closer to 1 is really looking ahead a lot further. And that's why it's a harder problem to do. It's harder to get things exactly right.
So then why in practice don't we always set gamma to be really, really small?
Yeah, that's where I thought you were going to go. So it's a good question. I mean, one of the things that happens if you set gamma to be something very close to 0 is the agent who's acting in the world acts very myopically, very like short-term thinking. So, I feel like eating now instead of finishing recording this lecture. So, I might as well just do that. Right? So you get short-sightedness.
I am eating now.
Well, that's good for you. I am not eating now. I would like to eat now, but I won't because I'm sufficiently farsighted to know that just getting something yummy to eat right now is going to interfere with my ability to finish this course because our, wonderful and talented video editor eventually is going to stop processing this stuff, and then we're hosed. So, yes, smaller gamma means easier problem, but more short-sighted behavior. Closer to 1 gamma is looking ahead more into the distance, but can make the computations more difficult.
Okay, so it's basically what these 2 results are saying is that there's a trade-off between horizon and sort of feasibility of solving a problem in a reasonable amount of time.
Yeah, that's a good way to say it. So here's a third useful fact that I probably should have put first now that I write it down. And that is the idea that if we start off with some Q function, Q1, and we run k steps of value iteration, in other words, we apply the Bellman operator k times, that the k-step Bellman operator is a contraction mapping, and the index of contraction is like gamma to the k, which is a much, much smaller number. So running k steps of value iteration actually pushes your value functions much closer together than, say, a single step of value iteration, which is really what you'd expect.
That is, although that's even better, right? Because it's not like linear.
It's not like linear.
Right, it's like gamma squared, gamma cubed, gamma to the third, gamma to the kth.
Right, and that is the index of contraction. So we run 10 steps of value iteration. That's like running 1 step of 10-step value iteration. So again, it's not super surprising, but what's nice about it is it gives us a way of quantifying how long we run value iteration and connecting it with how close you are to optimal after you've run that far. And so this kind of fact is underlying these other things that I wrote, number 1 and number 2, which is probably why I should have said the third one first.
That's okay. We can fix it in post.
So we talked a little bit about value iteration, and we said that it eventually identifies an optimal policy in polynomial time in 1 over 1 minus gamma. And I pointed out that 1 over 1 minus gamma isn't really a polynomial in the number of bits that it takes to write down gamma, because you can, with very few bits, specify a number that's very, very close to 1, causing this value to explode. So, in fact, value iteration doesn't give us a polynomial time algorithm for solving MDPs. There's only one way that we know to solve MDPs in polynomial time, and that is, dun-dun-dun, linear programming.
Okay.
Do you know what linear programming is?
I'm going to say yes.
All right. So it's an optimization framework in which you can give linear constraints and a linear objective function. And in polynomial time, as long as the number of variables and constraints is polynomial, get a solution.
That's exactly what I was going to say.
Yeah. Well, this is why I was going to say it for you.
Thank you.
So if we're going to use this idea to solve Markov decision processes, we need a way of encoding a Markov decision process solution as a linear program. So we need to encode our MDP as a linear program. So linear constraints and a linear objective function. So how do we know how to solve an MDP?
We just have to solve the Bellman equations.
Bellman equations, right. So I can write the Bellman equation in terms of the value function as a set of equations where the variables are the value function that we're interested in. So for each state S, we have a variable v sub s, and we relate the v sub s's through this equation to the v sub s primes, which are themselves just v sub s's, just ordered in a different way. And that seems really good, right? We have a set of constraints, and if we could just solve this set of constraints, we'll be good to go. So are we done? Do we have a way of doing this with linear programming directly from this expression?
Not if max... Unless max has become linear since I last looked. No.
Right, which they're not so much.
Mm-hmm.
Yeah. So since the max over actions is not a linear operator, this isn't translatable directly to a set of linear equations and a linear objective function. We have a system of nonlinear equations, but that's not so good. So the cool thing about max is that we can actually think about max as being specifiable in terms of a set of linear constraints and a linear objective function. Let's think of it this way. So let's say that we're trying to compute a max, and this is just as a simple little concrete example. Here's a thing that we're trying to compute the max of, and the max is going to be some value x. What is the relationship between x and all these values? So what's the relationship between x and -3?
X is greater than -3.
Greater than -3, or in general we could say greater than or equal to.
I knew that's what you were going to say.
Yeah, it's always nicer to have or equal to. It's more inclusive that way.
Mm-hmm.
And we can say the same thing about 7, right? X is going to be greater than or equal to 7, and x is going to be greater than or equal to 2, and x is going to be greater than or equal to 5. And how do we know this? Because it's the max of those. So it has to be at least as big as any one of them, right?
Right. By the way, your bottom thing says equals.
Greater than or equal to.
Mm-hmm.
It could be equal to 5 if I get rid of the 7.
Yes.
All right, so this is a set of constraints, of inequality constraints, right? So is it true that now the solution to this set of inequality constraints is exactly the max?
No.
And why is that?
Because 9 is also greater than or equal to all of those things.
It is, and 9 is the max of these things.
No, that's not quite true.
No. So what do we have to say? We have to say that it's bigger than or equal to all these things, and of all the things that are bigger than or equal to all these things, we want the smallest such x, right? We want the x that's as small as possible while still satisfying all these constraints. In this case, that's going to have to be 7.
Right.
Right? Because 7's bigger than all the other ones, and you can't get any smaller without getting smaller than 7.
Right, and of course, min is a linear operator, so we're good.
No. Min is an objective function. This is a linear objective function. This is okay.
Ah, good.
So that's what we're going to do. We're going to generalize this idea to the equations in the Bellman equation in a very similar way.
I look forward to it.
So we can get part of the idea really simply by just replacing this equation with something that says for all state and action, the value at a state is bigger than or equal to this expression. This is essentially the Q value. For each SA, this is the Q value SA.
Mm-hmm.
So that's good. Now what we have to add that min thing. So what do we minimize here?
V.
So we can't just minimize V like that, because that's a vector.
Right.
And we can't just minimize V sub S, because S is unbound here, right? It's like which S? Which S do we want to minimize? So we kind of want to minimize all of them somehow. So the way we're going to write that, and this turns out to work, is minimize the sum. So that's going to put pressure on all the individual v's to be as small as they can be so that it actually equals the max, isn't just an upper bound on the max.
Right, because if any one of them isn't, then you don't have the minimum sum.
Right, then you can always move it down a little bit.
Right.
So this actually is a linear program that is the solution to which is equivalent to the solution to the MDP. So we can just write down this linear program and give it to a linear program solver that runs in polynomial time, and boom, we get our values v sub s. How do we get our policy from that?
We just choose the action that always in expectation gives you the best value. Just sort of one step look ahead.
Yeah, we choose the greedy policy with respect to that optimal value function. So this is cool. This is sometimes called the primal, I guess because it lives out in the woods, representation of the linear program for solving MDPs. And this is a perfectly reasonable, this is actually very useful from a theoretical perspective. I haven't seen too many people really use linear programming to solve MDPs. It's got some overhead associated with it that seems to make it a little bit difficult to get it to run competitively with the other algorithms. But it's okay, especially if you have a really good linear programming package. And if you happen to have other kinds of linear constraints that you need to throw in, this is a very convenient way of solving slightly more difficult problems, MDPs plus a little bit of extra constraint. So does that make sense? You good with that?
Yeah, I'm good with that.
All right. I want to say one more thing about linear programming by switching away from the primal to what's called the dual. So linear programming has this nice property that you can actually, any linear program, you can change the constraints into variables and the variables into constraints, and you get a new linear program that's equivalent to the old one. So this is just true in general for linear programming. It's linear programming duality. And sometimes it's a really useful way of actually solving them and for putting bounds and constraints on the solutions. But in the context of MDPs, it actually does something kind of cool. So I want to show you that.
Okay. Is it going to be as cool as what happened when we did support vector machines?
I don't remember that.
We did the same thing. We wrote down a series of equations and we solved for the dual.
Nice. So yes, it'll be the same amount of cool as that.
Excellent. Excellent. I look forward to it.
So the process of producing the dual of a linear program is just a mechanical process. There's a series of steps that you go through where each constraint from the primal becomes a variable in the dual, and each variable in the primal becomes a constraint in the dual, and certain maxes become mins, and bounds become objective function things. So what I've done here is I've actually gone through that process, which we could go through in detail, but let's just pretend that we did, and we create a new linear program from the old linear program, and the new one is called the dual. So let's take a look at this dual in detail, because it turns out that the variables and the constraints actually have some very nice interpretations that are worth thinking about. Here in the dual, the thing that we're trying to optimize is we're trying to maximize the sum over all state action pairs of the reward for that state action pair times this value QSA, little QSA. So little QSA, probably not a great name for it because it's not the same as a Q value, but it's something. It's something that we're multiplying by the rewards and we're trying to maximize it. So one way I like to think about QSA is as policy flow, sort of how much agentness is flowing through each state action pair. If it follows the policy, it's going to spend some time running around in the environment, passing through each state action pair. And each time it passes through a state action pair, we're going to get the reward associated with that state action pair. And what we want to do is maximize that reward. So from this sort of policy flow concept, it sort of makes sense what it is we're trying to maximize. It's in some ways even more intuitive than in the primal, which we were saying we're trying to minimize the value, which of course we're not really trying to minimize the value. We're just trying to minimize it so that it doesn't end up being an upper bound on the value. Here we're actually trying to maximize expected reward, which seems like a really good thing.
Right.
Okay, so this is now going to be subject to the following idea, that for each state, in this case it's easier to think of them as next states. For each possible next state, we want it to be true that the amount of policy flow through that next state, summed up over all the actions that are going through it, that should be equal to, in some sense, the number of times that next state is visited, which we can get by summing over all states we might have started at and actions we might have taken from there, the policy flow through that state action pair times the transition probability that would send us to S prime as a result of that. And we're going to also include in this equation sort of the sense that we can also start at a given state action pair. So we're just going to stick a 1 in for that. So there's some policy flow that we're injecting into each state action pair of the system. And we're going to add to that any policy flow that would be coming through it through other parts of the system. So it's kind of like we're dumping policy flow all over our MDP and then letting the MDP kind of pump around what's left. And it's discounted. There's a little discount here. So there's actually, evaporation or something happening all over the place. And what we want to know is, what's the way of letting the flow go through, of kind of deciding at each state which action it should flow through so that we ultimately get the maximum possible reward.
Mm-hmm.
And I think just one additional constraint here, just to make sure that the policy flow is non-negative, so that we can't introduce a whole lot of policy flow in one place and then drain it out some other place to make things balance.
Right.
You can think of these constraints as actually being a kind of conservation of flow, right? So the amount of stuff going into S prime has to equal the amount of stuff coming out of it. And that's all this is saying, right? It's just saying that has to balance, that has to be a meaningful flow. Subject to that constraint, maximize reward. So again, this is kind of a neat interpretation of what it means to solve a Markov decision process, but it just comes mechanically out of the primal version of setting up this as a linear program.
Okay. Does that suggest an algorithm that's different from the sort of algorithms we've been using so far?
Interesting thought. So, well, for one thing, it is an algorithm, right? In the sense that once we've set things up this way, we can hit it over the head with a linear programming stick and a solution will come out.
Sure.
And in fact, it'll come out in polynomial time, which is nice.
Mm-hmm.
But you're right. I mean, in some sense, if you think about value iteration as something that's propagating these values around, this has a different form. This is really concentrating more on the policy aspect of the MDP. And maybe we could make an algorithm that more directly kind of searched in policy space for the best behavior for the MDP.
Let's do that.
Charles, I'm going to say that you invented an algorithm just now that we're going to call policy iteration. It's kind of like value iteration, except it's going to iterate in policy space.
I'm so smart.
Yeah, though you invented it a little bit too late because it dates back to, 1960 or thereabout.
Dijkstra? Dijkstra always has ideas before I do.
Yeah, Dijkstra's pretty clever, but this was actually Ron Howard.
You mean the Ron Howard, the director?
Oh, sorry, no. It's the Ron Howard, the algorithm designer.
Oh, that one. I always get them confused.
One played Opie, and the other one proved contraction mappings.
They're very similar things.
So this is what I was imagining you were explaining. Here, let's take it step by step. So what we're going to do is we're going to start off picking an arbitrary Q function, like we often do. We'll call that the initialization step. Then we're going to iterate the following. We're going to take the teeth Q function and compute its greedy policy, call that pi sub t. Then that policy, we're going to evaluate it to get a new Q function, qt plus 1. And then we're going to repeat and iterate this over and over and over again. So each time we go around this loop, we're taking our previous Q function, finding its greedy policy, taking that greedy policy, finding its value function, and repeating.
Lather, rinse, repeat.
Exactly. So unlike when I take a shower, we actually get convergence in finite time. So in particular, the sequence of Q functions that we get converges to Q star, which is good. That's like how policy iteration works.
Mm-hmm.
But even better, the convergence is exact and complete in finite time. Though I guess that was kind of true of value iteration as well. And it converges at least as fast as value iteration in that if at any point we sync up the Q functions, we start value iteration and policy iteration from the same Q function, then each step that policy iteration takes is moving us towards the optimal Q function no more slowly than value iteration does.
Okay.
So that kind of suggests that this is just, way better.
Yeah, isn't it way better?
So why is it not way better? There's kind of some excitement going on in here that we need to take into consideration. There is a bit of a trade-off, as you like to say.
Mm-hmm. What's the trade-off?
So where's the trade-off here? We're getting faster convergence at the cost of greater computational expense. So in particular, this step, this policy evaluation step that says take the policy and then work out the Q function for that policy, you can do that by, say, solving a system of linear equations, or perhaps more commonly, by running something kind of like value iteration to completion. So in the inner loop of policy iteration is something that's an awful lot like value iteration. And so maybe it's not so surprising that it goes at least as fast as value iteration. It's doing a lot more work than value iteration. Each iteration of policy iteration is doing pretty much all the work of value iteration.
Yeah, well, so it just depends upon what you're counting. I say we just count the outer loop.
then we win, or at least we don't lose. In fact, this is kind of an interesting, outstanding question. So we don't really know how many iterations policy iteration takes. So an open question is what the convergence time really is. We know a couple things about it, but it turns out to be fairly weak. We know that there are some MDPs such that the number of iterations that policy iteration takes is linear, at least as large as the number of states in the MDP. Though I don't think anybody's actually shown like 2 times the number of states. So there's all we know is something really, really basic, which is that it takes at least number of states iterations in the worst case. And we know it can't be any worse than number of actions raised to the number of states, an exponential. But where it sits in between, we don't really know. And so if it's closer to linear, then it's totally awesome and it blows the doors off of value iteration. If it's more like exponential, then it's probably still better than value iteration, but it's definitely more of a wash. What I'd like to do, and I'm guessing that maybe you don't want me to, but I'm going to try to do it anyway, is go through the argument as to why policy iteration actually works. I think ultimately it's not that bad, but we're gonna kind of slog through it. And so one of the things that we're going to need is the ability to compare policies to each other and value functions to each other. And so we're going to introduce a concept of domination.
Oh, yeah.
So this is what domination means in the context of policies. We're going to say that policy 1 dominates policy 2 if it's the case that for all states, the value of that policy at that state for policy 1 is bigger than or equal to the value at that state for policy 2. So it could be that there's some policies where policy 1 does better in one state and policy 2 does better in another state, but if it dominates it, policy 1 has to do no worse in any state. And in fact, we're going to say we have strict domination if it's the case that policy 1 dominates policy 2 and there's some state for which it's actually strictly better. It's not equality.
Okay.
And just for fun, we'll also introduce the concept of epsilon optimal policy. So policy is epsilon optimal if it's the case that the value function for that policy is epsilon close to the value function for the optimal policy at all states. And so what this does is it gives us a concept of bounding loss or bounding regret. So we'll say that a policy is nearly optimal if the amount that it loses essentially per time step is very small.
Okay. So, by the way, does this mean that if policy 1 dominates policy 2 but does not strictly dominate it, they must have the same value everywhere?
Yeah, that's right. They'd have to have it would never be greater than. It would always be greater than or equal to, which means it's always equal to. So 2 policies that, well, what you said.
Oh, okay. Good. Well, as long as it's what I said.
In addition to this notion of domination, another thing that's going to be helpful is if I tell you a tale of 2 operators for 2 policies. So imagine we've got policy pi 1 and policy pi 2. We're going to define the one-step Bellman operator on those 2 policies. So the first operator, B1, when we apply it to a value function v, is just going to return for each state the immediate reward from that state if we follow policy pi 1 plus the discounted expected value for following policy pi 1 with one-step lookup on v. So we're converting v. We're basically putting v through one step of value iteration with a fixed policy pi 1. And b2 is the same idea, same operator, except with respect to policy 2. Pi 2, pi 2. Okay? So what we're going to be able to show is various kinds of interesting domination relationships between the value functions that we get out with each of these operators. All right, so now we've got these 2 Bellman operators, b1 and b2, that each one is associated with a fixed policy. So b1 makes an update essentially following pi 1, and b2 makes an update following pi 2. So we know a bunch of things about these updates. So, for example, we know that if we apply b1 to 2 value functions, what's going to happen to the value functions as a result?
They will not move further apart.
By a factor of at least gamma.
Unless they're the same one, right? If they're already perfectly together, then they won't move closer together.
Because they were at a fixed point. But then the distance is 0, and we do get gamma closer to 0 because 0 times gamma is still 0.
Sure. So that's true, but I'm just saying it's not that they always get closer together.
Yeah, okay. All right. That's fair.
Okay.
That's fair. If they're not on top of each other, then they get closer together.
Mm-hmm.
And the same thing is true of B2.
Yeah.
But there's some other interesting properties of these that aren't necessarily true of the standard Bellman operator, but they are true when we use a fixed policy like pi 1 or pi 2. So let's step through what some of those properties are, and we'll use them to show that policy iteration behaves itself.
Nice.
So this is the property that we want to show that B1 and B2 have. So if we've got two value functions, V1 and V2, not only if we apply these Bellman operators to them do they get no farther apart and actually potentially closer together, but they actually keep their same ordering. So let's say that V1 dominates V2. So V1 is bigger than or equal to V2 at all states S. Then that still is true after we've applied Bellman operator B2 or Bellman operator B1, but we're talking about B2 right now.
Okay, well, that makes sense, and I think it follows immediately from raising Thursday to the Monday power.
Oh, I see. No, that's supposed to be theorem. Sorry about that.
Oh, okay.
Yeah, we don't do day of the week math until the next section.
Oh, okay. Looking forward to that.
So how would we show something like this is true? The standard thing that we always seem to do is go back to the definitions and just plunk things through, and let's see what we get.
Okay.
To show that B2 V1 dominates B2 V2, I'll just subtract one from the other and see if the result is always non-negative.
Okay.
So let's do that. We plug in the definitions, and I did some canceling here because it always sort of comes out the same. This sort of notion that since we're talking about the same states and the same actions, these rewards are going to cancel. The gammas and the summations and the transition probabilities are going to factor out, and we're going to end up with something, well, actually a lot like this. Gamma times the sum over all states of the probability of reaching the next state times the difference at the new state S prime between the value functions V1 and V2.
Oh, okay.
And what do we know about this quantity here?
Well, we know that V1 is always greater than or equal to V2, which means that V1 minus V2 has to be non-negative.
Good. And then we take a convex combination of a bunch of non-negative values. There's no way it could become negative.
Right.
Could be 0, I guess. But we know that we're greater than or equal to 0. We can't be smaller than 0. So that gives us actually exactly what we need, that if V1 dominated V2 before, B2 V1 dominates B2 V2 now.
Nice. And that if we replaced B2 with B1, this would also be true.
Yes, exactly so. The only thing that we're actually using here is that we have a fixed policy. It doesn't matter what the policy is. So B1 and B2 are the same operators, except they just differ as to which fixed policy they're using.
Okay, so both B1 and B2 have mono. That's perfect.
No, no, they don't have mono. They are monotonic, meaning they preserve this kind of ordering property. Not that they have mononucleosis, sometimes known as the kissing disease.
Well, maybe where you're from.
So we're going to need one more interesting property of this operator B1, but this one is specific to the context of policy iteration. So let's think about it this way. Imagine we've got some policy, pi 1, just like we've been saying, and associated with pi 1 is the operator B1, and let's say that Q1 is the fixed point of B1, right? And how do we know that it has a unique fixed point?
Because you proved it earlier.
Yeah, and it was the contraction property of B1.
Yeah.
So let's imagine that's happened. We've solved out Q1. And this is sort of how policy iteration works too, right? You start off with a policy, you get the value function of that policy. Then we're going to take the greedy policy, pi 2, with respect to Q1. So in the last slide or so, pi 1 and pi 2 were just arbitrary policies. Now pi 2 is specifically the greedy policy with respect to the value function defined by pi 1. So then let B2 be the operator associated with pi 2. And this is the thing that we want to show. The Q function that comes from solving for the fixed point of pi 1, so the value function for pi 1 is less than or equal to B2 applied to Q1. So does that make sense? So if we take whatever we end up with after we solve for the value function for pi 1, we take pi 2's greedy policy, and then we do one Bellman backup with respect to that, and we get a value function that dominates Q1.
Okay, and that's because of other stuff on the slide.
Yeah, so we'll just work through that. So intuitively what we're saying is we do policy evaluation on pi 1, we get some value function Q1, and then we do one step of essentially value iteration using the greedy policy with respect to Q1, and that's going to make it no worse, possibly better. And so the reason for that is, well, what is Q1? Q1, it's the fixed point of the B1 operator. So in this particular case, it's the reward plus the discounted expected value for taking action pi 1 and then ending up in some new state S prime and taking action pi 1 of S prime from that state.
Mm-hmm.
But think about what pi 2 is. We can actually substitute pi 2 for pi 1 in here, but pi 2 is the greedy policy with respect to this. In other words, it is the policy that causes this exact quantity to be maximized. That's what the greedy policy does. At every state, either we're going to do no worse than we did with pi 1, or we might actually do better by switching to pi 2, the greedy policy with respect to Q1. So at each state action pair, we're doing no worse by doing one Bellman backup with B2 on Q1. So this is exactly the result that we get, that the Q function that we had before is less than or equal to the Q function that we had before pushed through the B2 operator, right? The Bellman operator with respect to the greedy policy with respect to Q1. Essentially the idea is if we're going to do one more update on Q1 and we're going to do that update with respect to a policy that we know is greedy with respect to Q1, then we're moving up in the world.
Oh, I see. Okay.
What?
Well, no, I was sitting there thinking, well, shouldn't this be greater than or equal to? And then I think, oh, no, I see. I was kind of reading it backwards.
Yeah, I wanted to write it as, because domination up to this point we used greater than or equal to, but it just didn't feel right to put it this way, because it would have been B2 applied to Q1 is greater than or equal to Q1, which is true, but the ordering feels backwards to me. So this seems better, that we're going to take Q1, we're going to apply the B2 operator to it, and it's going to make things better.
Write it the other way and see what happens.
Sure.
So when I look at that, that says that applying the greedy operator to Q1 makes it better than it was before.
All right, so if that is more helpful for you to read, it's really the same thing. So that's great.
Oh, no, it is the same thing. I just realized the whole time you were talking, I had been flipping the thing in my head.
Sorry about that.
Oh, no, it's not your fault.
So now we have all the pieces we need. We had one property, we called it monotonicity. We should call this property something too. Value improvement.
Okay.
So now with value improvement and other stuff like the definition of pi2 and B1 and B2 and Q1 and Q2 and the monotonicity property, we should have all the things we need to prove that policy iteration moves in the right direction, that it actually improves the policy. Or in the case where the policy is already optimal, it can't improve it, but it doesn't break it, leaves it the same.
Mm-hmm. It doesn't ever make it worse.
Now we have all the pieces to put together a proof of policy iteration, and since you have all the pieces, you should be able to do it yourself. So here's what I'm doing. Let's take one step of policy iteration. That is, we start with some policy, pi1, and just for notation, we have Bellman operator B1 associated with that policy, and Q1 as the fixed point of that operator. And then Q2 is the next policy we get. It's the greedy policy with respect to Q1 that we had from the previous iteration. And just again, for notation, B2 will be the Bellman operator for that policy, and Q2 its fixed point. And ultimately, what we want to show is that the Q function that we get for the second policy dominates the Q function that we get for the first policy. And so this is how we're going to do it. We're going to have a series of steps, and each of them has a justification that we've been talking about recently. Just fill in the boxes.
Good. I think I understand what you want, and I think I can do it.
Yeah, and we'll try to be a little bit generous with the names of these justifications, but I did give names of these steps in some of the previous slides, so I'm hoping that those words should still be jumbling around.
Some of them, anyway.
The first statement that we need to make this proof go is that B2, the operator B2 applied to Q1, dominates Q1.
Right, which you just proved like a slide ago, right?
Right, and what did we call that?
Value improvement.
Good. Yeah, the fact that we're using the greedy policy with respect to Q1, one step of update with respect to that gets us a possibly better value function.
Right.
Great. Now, the next statement says that if we iterate this operator, so B2 iterated k times applied to Q1 versus B2 iterated k plus 1 times applied to Q1, the k plus 1 dominates the k1. So this is kind of a step of a proof by induction. But what's the main justification here? What lets you make this statement that one additional application of B2 is going to dominate the previous adaptation?
So I'm going to say that it's the other thing that you said, because I only remember two things that you said. And so that would be monotonicity. It's the monotonicity of B2.
Right. But if you've used up all of these, the next two boxes are going to be hard. But just to go through why this is the case, what we've done is we've taken this first equation and applied B2 to both sides.
Mm-hmm.
Just over and over and over and over again. But since one dominated the other, after we applied B2 to it, it still dominates.
Right. That was like 2 slides ago. That was the whole point of monotonicity. And they look very similar. Value improvement and monotonicity look very similar to one another.
Exactly. And they all ground back out in domination.
Right. Everything comes down to domination.
Boom.
Nice. Very nice. Very nice. Okay, cool. All right. So we got value improvement, although I guess that's more accurately value non-deprovement or something, just to be, mathematically technical here. And then we got monotonicity.
I like how you became more mathematically correct and less grammatically correct.
Well, those things are trade-offs. They're fundamental trade-offs. Okay, so we got that. So we got value improvement. we got monotonicity of our value improvement, so to speak. And so that's actually what the third thing is. It's basically the monotonicity of our value improvement. You just kind of kept saying, if I keep doing the second thing over and over and over again, it keeps getting better and better. Therefore, the very last one that I do has to be better than the very first, or at least no worse than the very first one that I did. So I guess that's, there's a math term for this. Transitivity, A greater than B greater than C, A greater than C.
Oh, that's right.
It's the transitive property of monotonicity, non-deprovement.
I wouldn't say that. It's what we get each time we iterate this B2 operator. We are getting something that dominates the previous value that we had, which dominates the previous one, which dominates the previous one, which eventually grounds out in this first statement, Q1. So if you just chain all those together, we get, for each of the possible Ks, number of iterations that we could apply the B2 operator, we're just getting more and more monotonistically improved.
Right. So that's, but just to remind everyone, that's just if A is greater than B and B is greater than C, we know that A is greater than C. Right. Transitivity.
Yeah, that's just using transitive, but we're using it over and over and over and over and over.
Yeah, but it doesn't matter. A greater than B greater than C greater than D greater than E greater than F greater than G.
Got it.
Okay.
Great. And then the last statement says, okay, well now, because we know that's true, we know that Q2 dominates Q1.
Right, and that's because you said way up there at the top that Q2 was the fixed point of the B2 operator, and the limit of K approaching infinity, Bk of Q1 is in fact the fixed point.
Good. So it's the definition of Q2 as the fixed point, and this sort of notion that we can just keep repeating this operator and we get to the fixed point eventually. Does it matter that there's Q1 plugged in here?
No, it does not, because you defined it that way.
Not that we defined it. Well, up to this point, we came through Q1, but ultimately, the fact that we get to Q2 doesn't matter that we started at Q1 because there's a unique fixed point. So no matter what value function we start at, if we keep applying these operators over and over and over again, we're going to get to Q2.
No matter what.
And so we did.
Yeah, but we want to be able to relate it to Q1, and doing it this way allows us to do that in 3 easy steps or 4 easy steps.
Yeah, 4 slightly easy steps, 1 slide per step. But that's exactly right. So we related Q2 and Q1, which is to say we've related 2 adjacent steps of policy iteration to one another. Each time we do a step of policy iteration, we get no worse. This doesn't tell us that we can't reach some kind of local optimum, but it is telling us that we're getting no worse as we apply this series of operators.
That's nice. I like that. So this is a pretty straightforward derivation of fixed proof through transitivity of value non-deprovement monotonicity.
Yeah, obviously.
Okay, I like proofs. I like obvious proofs.
I like the word non-deprovement.
We have to use that. That'll be the name of our band.
The really important thing here is that policy iteration does not get stuck in the local optimum. That is to say, if there's any way to improve, it will actually improve. It won't get stuck before. So the important step in the proof for that is actually back 1 slide when we talked about value non-deprovement, or what I called value improvement. So I went back a slide so we can look at this together. So this is the claim that I'm making, Charles, that if it's the case that pi 1 is optimal, then the greedy policy pi 2 with respect to the fixed point of the pi 1 is going to be the same. We're actually going to be stuck at the fixed point because that's the whole thing about being a fixed point. But if it's not, then there has to be at least one state someplace where this value non-deprovement is actually value improvement, like strict value improvement for some state like that. Boom.
I see. So what's really going on here is we should be more precise maybe about what value improvement really means or what value non-deprovement means.
Okay.
We're talking about it, every time we talk about it in terms of one value function better than another. And so it's easy to think of it that way. But if that were the case, then I could have sort of cycles, right, where I have 2 states where I keep on each iteration swapping back and forth which one is better than the other, and you'd still have domination in both cases, right? Does that make sense, what I just said?
Wait, no, because domination is point-wise, it's state-wise.
Yes, it is state-wise, but imagine I had 2 states, let's call them S1 and S2, and let's say for one particular value function, if I were going to compare, let's say Q1 and Q2, or V1 and V2, it's going to compare V1 and V2, it turns out that in S1, V1 is greater than it is in V2. So just make up some numbers, right? And in the other case, they're the same.
The same.
Yeah.
Okay.
Then I could apply an operator to both of them. It would also be the case So here V1 dominates V2, right?
Right.
So here's another set of numbers I could write down where V1 still dominates V2.
Okay.
So rewrite the S1 and S2 again underneath.
All right. So V1 still dominates V2.
Right. So V1 still dominates V2 if I just swap the two rows around. And so if you weren't thinking carefully about what value improvement or value non-deprovement meant, you would think that you could just go back and forth between these two different values where 10.6 and 3.3, those rows sort of swap, because in both cases, you're still getting V1 dominating V2. But it's actually the case that the way this value improvement works is that it's true not just for the overall value functions, it's true at every state.
Oh, I see. Yes, that it can't be the case that we go from V1 have S1 being 10 to V1 S1 being 3 because it's actually non-deproving.
Right.
In other words, we can't go down. We can stay the same, but we can't go down.
Right. So the statement has to be the case for all the states as well as the overall set of states. So once V1 is better than V2 in some state, it basically has to stay that way.
Got it.
So this keeps us from cycling back and forth, and this is what keeps us from getting in a kind of get sort of locally stuck. That's my claim.
Okay. All right. So local stuckness doesn't happen.
Mm-hmm.
And in particular, we get strict value improvement in at least one state if we haven't actually reached the fixed point yet. And therefore, each time we go through policy iteration, it's actually getting better until it can't get better anymore. So one other interesting thing to point out is that the number of policies, each time that we go through an iteration of policy iteration, we have a new deterministic policy. There's just a finite number of them. Therefore, at some point, we exhaust the set of possible improvements that we can make, and we have to have found the optimal policy.
You know what that reminds me of?
EM.
Oh, close though.
Okay.
Reminds me of the proof we had for why k-means had to converge.
Oh, yes. It's exactly the same argument. Yeah, when we talked about k-means in the other class, we talked about how there's a finite set of assignments that can be made, and each time you do an iteration of k-means, we get either the same assignment or one that has a better score, and therefore we're going to find the one with the best score.
Well, we're going to find A1 that doesn't change anymore. But the difference between k-means proof and this is that you could get stuck in a local optimum.
In k-means.
K-means, but here you can. And I think the big difference is that you basically, its statement of value non-deprovement is at every single point, every single state in this case. Whereas with k-means, that wasn't necessarily the case.
Okay, super. So do you feel like you have you're grokking policy iteration now?
Yeah, in particular, I'm grokking that it actually kind of has to work. That's sort of cool.
Cool. I think we can sum up then.
Let's sum up. I like summing up.
So in this section on advanced algorithmic analysis, what have we learned?
Well, we learned a bunch of stuff. It's kind of I'm going to say a compact and dense lesson. I think that's pretty good.
Oh, that was a math joke, wasn't it?
Yes, it was. It was a math joke. Well, first thing we learned is that you like alliteration. This whole section was advanced algorithmic analysis.
Okay.
And in particular, we talked about three things, all ending in I: VI, LI, and PI.
Yeah, there's a problem with LI, though.
Yeah, that's not really a thing.
Yeah, it's LP, linear programming.
But then it wouldn't end in I.
I agree with that, but at least it ends with P, and the other one starts with P. So there's some overlap. All these things overlap with each other.
Well, if you call it a VLP for very linear programming, then you could...
Yeah, no, it's just linear programming. Let's just go with that.
Okay. All right. I mean, very linear is still linear. In any case, all right. So what did we learn? So we learned a little bit about each of those things. So particularly for value iteration, we learned that it converges to optimal in finite number of steps, or, gets bound towards that.
Okay, can we be more precise there? The value function doesn't converge in a finite number of steps.
But the policy does.
The greedy policy does, yeah.
Right. But really, that's what we want.
Yeah, I agree with that.
Sure. But that's a good point, that it's not that the value function itself has to, because otherwise we'd go all the way back to EM and have that conversation again, but that the policy itself will stop changing. The greedy policy will stop changing at some point and in finite time.
Right. And it'll be optimal at that point. Yeah, and the value function itself doesn't necessarily converge, but it's going to get boundedly close to the solution. So that is to say, if we want to be epsilon close to the solution to the Bellman equation, we can define how many iterations of value iteration we would need to accomplish that degree of approximation.
Right. And that's fine, because in the end, that's interesting. But what's really interesting is that we get a policy that we can act on.
because we want to maximize reward. That's just what we're about.
That's what we're all about, really. So let's see. Then we talked a little about linear programming, which is yet another way to think about solving MDPs. And what I remember most about it is you actually defined the dual.
Okay.
And that was really cool because it allowed us to solve the problem. And like so many things that we do, it was a callback to our first class. And now I actually understand how support vector machines work.
Okay. I think you did that lecture, so I'm hoping you understood it already.
Well, there was just a point where you said, well, or you could solve the dual. And then I like rapidly waved my hands and said, don't worry about it. It's a dual. It's a thing.
Okay.
But now we talked about the dual. So I think that that's good.
I feel like the concept of dual is somehow relevant to superheroes.
You think so?
I don't know. Like, you know way more about comic books than I do, but isn't there like
I do.
every superhero has a dual, like anti-Batman or the Dark Spider-Man?
Venom. So you're saying that primal and duals are like they're like nemesis.
Yeah, or mirror images of each other in some way.
So the flow, the sort of policy flow idea, is like the nemesis of the value idea, or the mirror image of it.
Yeah.
Sure, let's go with that. I was thinking more of a hip hop analogy, but I think that's pretty good.
Oh, flow is a hip hop thing.
It's a hip hop thing.
And values. People in hip hop have values.
That's right. So it just follows in one step. Okay, speaking of one step, so then there's policy iteration, which I thought was kind of cool. We got a chance to prove a bunch of things about it, and I think the first thing we talked about there, or somewhere in that mix, was domination, which turned out to be really cool.
Yeah, and that comes up actually in all the algorithms. Value iteration has some of that, linear programming has some of that, and policy iteration. The proof of policy iteration depends pretty significantly on that.
Right. Speaking of things that the proof of policy iteration depends on, we also talked about value non-deprovement, or value improvement, I believe, is the non-technical term for it.
That's right, and we argued that we'd actually get strict value improvement anytime that we didn't have a policy that was already optimal. If it was already optimal, then a step of policy iteration resulted in value non-deprovement, which is just our broken way of saying it doesn't get worse. It might not get better, but it doesn't get worse.
Yeah, it's like a monotonically non-decreasing function. But the other thing is, we had a discussion that I think is actually pretty important, that when we talk about things like domination, we were writing them down for good notational reasons, talking about an entire value function, but really this is about things have to also be true on a state-by-state basis.
That's right.
Because if that weren't true, then in principle, you could cycle, and then you could get stuck in local optima. But here, we don't get stuck in local optima because things also dominate on a state-by-state basis.
Cool.
Kind of neat.
Yeah.
So we also talked about monotonicity.
And that you can contract it from kissing.
Yes. Oh, you said contract. Very, very well done, Mike.
Oh, yeah, that was pun intentional, sorry.
Pun intentional. Okay, and really when you put all those things together, I think the real thing that we learned in this lesson is that proofs do not suck.
So that's great, because if I recall, we started our last class with a little discussion about how I don't mind proofs as much as you do.
That's right. Speaking of proof, you forgot the S on proofs. No. See, I did a proof of your proof. That was pretty good.
Oh, you proofread it.
Yes, yes.
Nice.
Oh, I feel like we've converged.
And that's what this was all about.
And that's what this was all about.
Yeah, there's something very satisfying about getting to the convergence point.
Very nice, very nice. Okay, well, I think that's everything that I was capable of learning in one lesson.
Yeah. All right. Well, so yeah, next time we'll start in with something else. I think we're going to talk about how we can modify reward functions and get different things out of them.
Oh, yeah, that's my favorite. Excellent. Well, then I will see you then.